Good afternoon, Dr. Jason. Today I will be presenting about house prices and transaction volumes in Malaysia. Housing markets play a key role in both economic stability and social welfare. Housing itself is a dual purpose asset. It provides shelter, but it is also an investment driven by expectations of capital gains. As a result, house prices and transaction volumes often move together, but the direction of their relationship is not always clear. Evidence from markets such as Hong Kong suggests that rising prices tend to stimulate transactions, rather than transactions driving those prices, which raises important questions about the effectiveness of demand-side housing policies. In Malaysia, house prices have continued to rise, even though housing transactions often fluctuate and policies mainly aim to reduce demand. However, empirical evidence for Malaysia remains limited. This study, therefore, examines the long-run relationship, short-run dynamics, and granular causality between housing price changes and transaction volumes, using robust time series methods, with the aim of informing housing policy more effectively. Motivated by this gap, this project seeks to answer the following research questions. First, is there a long-run equilibrium relationship between housing prices and transaction volumes in Malaysia? Second, what are the short-run dynamic interactions between these two variables? Third, does either variable greater cost the other? And what does this imply for housing market policy? To address these questions, this, this project applies a combination of VAR-based methods, Johansson co-integration testing, the ARDL bounce testing approach, and the Toda-Yamamoto granger causality framework. This allows for a robust assessment of both short-run and long-run dynamics without imposing overly restrictive assumptions. By doing so, the findings aim to provide empirical insights that are directly relevant to Malaysian housing policy. This study investigates the causal relationship between housing prices and transaction volumes in Hong Kong, using VAR, Toda-Yamamoto granger causality, and ARDL bounce testing on data from 1993 to 2014. The key finding is a one-way causal relationship, where house price movements drive transaction volumes. The transaction volume does not influence house prices. The absence of long-run co-integration further supports the view that transaction volume is a consequence rather than a driver of house price changes. Based on these results, the authors argue that demand-side policies, such as stamp duties, are ineffective in controlling housing prices, and that government intervention should instead focus on the supply side to achieve long-term housing affordability. Moving on to the dataset overview. The data consists of quarterly Malaysian housing market information from 2009 quarter 1 to 2024 quarter 4. Two key variables are used: the house price index, which captures overall housing price movements, and the number of housing transactions, which reflects market activity and liquidity. To ensure comparability and interpretability, both series are transformed using natural logarithms. The house price index is then first differenced, producing the variable d-lon HPI, which measures quarterly house price growth, whereas the transaction variable remains in levels as lon trans n. These transformations serve two purposes. First, they help stabilize the variance of the series, and second, they align the data with the stationarity requirements of the econometric models used later on in the analysis, such as VAR, ARDL, and Granger causality frameworks. The final dataset therefore consists of the first difference of log house prices and log of transaction volumes, which forms the basis of all subsequent empirical analysis. To determine the order of integration of lon trans n, we first examine its stationarity properties. Initial unit root testing shows that lon trans n contains at least one unit root, indicating that the series is non-stationary in levels, and therefore it is not an I0 process. And to determine whether lon trans n is integrated of order 1 or higher, we apply a unit root test to its first difference series, d lon trans n. And visual inspection of the difference series shows that it fluctuates around a constant mean close to zero, with no visible deterministic trend. Based on this observation, the augmented Dickey-Fuller, or EDF test, is estimated without an intercept or trend component. The optimal lag length is selected using the Bayesian Information Criteria, or BIC, with a maximum of 10 lags considered. The BIC selects two lagged differences to adequately control for residual autocorrelation. To validate this lag choice, a jump box test is conducted on the residuals of the ADF regression up to lag 12. The p-value of 0.3055 exceeds the 5% significance level, indicating no residual autocorrelation, and confirming the adequacy of the chosen lag structure. The ADF test statistic for the difference series is minus 9.741, which is more negative than the 5% critical value of minus 1.95. Hence, we reject the null hypothesis of a unit root. This implies that the first difference series is stationary. Since long trans n is non-stationary in levels but stationary after first differencing, we conclude that long trans n is integrated of order 1 or an I1 process. The objective of this analysis is to determine the order of integration of the variable ln HPI. We begin by testing the presence of a unit root using the Dickey-Fuller and augmented Dickey-Fuller test. The choice of deterministic components in each test is guided by visual inspection of the time series plots, and hypothesis testing is conducted at the 1% significance level. Based on the time series diagram, ln HPI exhibits a deterministic trend and fluctuates around a non-zero mean. Therefore, the appropriate Dickey-Fuller specification includes both an intercept and a time trend. The model is rewritten in first difference form, where testing whether gamma equals 0 determines the presence of a unit root. The null hypothesis of the DF test states that the series has at least one unit root, with a test statistic of minus 0.7826, which is greater than the 1% critical value of minus 4.04. Hence, we fail to reject the null hypothesis. This indicates that ln HPI is non-stationary and contains at least one unit root. A key limitation of the Dickey-Fuller test is its reliance on the assumption that residuals are independently and identically distributed. If autocorrelation is present, the DF test becomes invalid. To address this issue, the augmented Dickey-Fuller test is used, which includes lagged difference terms to remove serial correlation. For the ADF test on ln HPI in levels, the Bayesian information criterion was used to select the optimal lag length. With a maximum of 10 lags, the IC selected 4 lag differences. Since the original series shows a trend, both an intercept and a trend were included in the regression. Before conducting hypothesis testing, we verify that the residuals from the ADF regression are free from autocorrelation. The jump box test confirms this, as the p-value exceeds 0.05. This indicates that the selected lag structure is sufficient and the ADF results are valid for inference. The ADF test statistic for ln HPI in levels is minus 3.8683, which is greater than the 1% critical value. Therefore, we fail to reject the null hypothesis and conclude that ln HPI remains non-stationary with at least one unit root. Since a trend specification was used, we perform a joint hypothesis test to verify whether the intercept and the trend are jointly significant. The F statistic of 10.5997 exceeds the critical value of 8.73, indicating that the trend component is statistically significant in the ADF regression. After confirming that ln HPI is non-stationary, we difference the series once. The first difference series fluctuates around a non-zero mean with no visible trend, so an intercept-only ADF model is used. The BIC selects 3 lagged differences to address autocorrelation. The ADF test on the first difference series of minus 0.9923 fails to reject the null hypothesis at the 1% level. This indicates that the ln HPI is still non-stationary, implying that ln HPI contains at least 2 unit roots. Since the first difference remains non-stationary, the series is differenced a second time. The second difference series fluctuates around a zero with no visible deterministic components, so a pure ADF model without intercept or trend is estimated. The ADF test on the second difference series strongly rejects the null hypothesis of a unit root. This confirms that the second difference of ln HPI is stationary. Since the level and first difference series are non-stationary, we conclude that ln HPI is integrated of order 2, or an I2 process. The ARDL framework is used to analyze both short-run dynamics and potential long-run relationships between variables. It is flexible in handling regressors that are either I0 or I1 process, but it cannot be applied when variables are I2. Therefore, this approach is suitable for our variables. When d ln HPI is treated as the dependent variable, the AIC with maximum lag length of 5 selects an ARDL40 model. Visual inspection shows no deterministic trend in either series, but both fluctuate around a non-zero mean, so only an intercept is included. The adequacy of the ARDL40 specification is verified using the ACF plots of residuals. Since all autocorrelations lie within the 95% confidence bounds, there is no evidence of serial correlation, confirming that the selected lag structure is sufficient. The selected ARDL40 model includes 4 legs of the dependent variable and a contemporaneous effect of ln trans n. This specification captures short-run dynamics in house price changes. To test for co-integration, the ARDL model is reparameterized into an unrestricted error correction model, or UECM. This allows us to jointly test for long-run relationships while retaining short-run dynamics. The bounce test yields an F statistics of 2.3291 with a p-value well above 5%. Therefore, we fail to reject the null hypothesis, indicating no evidence of a long-run co-integrating relationship when d ln HPI is the dependent variable. When ln trans n is used as the dependent variable, the AIC selects an ARDL11 model. Residual diagnostics indicate no significant autocorrelation, confirming that the lag structure is adequate. The bounce test, with an F statistic of 11.889, strongly rejects the null hypothesis of no co-integration, providing evidence of a stable, long-run relationship between ln trans n and d ln HPI. The estimated error correction term, or ECT, is negative and statistically significant, indicating that deviations from long-run equilibrium are corrected relatively quickly. Approximately 58% of the imbalance is eliminated in the next period. The long-run multiplier of 8.4159 shows that sustained changes in house prices have a strong cumulative effect on housing transactions, indicating that the market is highly sensitive to long-term price movements. Overall, the results showed an asymmetric relationship. Transaction volumes adjust to long-run price movements, while short-term price fluctuations do not establish a stable equilibrium. Or, in other words, the short-run price changes have temporary effects only. This suggests that the housing market responds more strongly to persistent trends than to temporary shocks. This section examines the direction of Granger causality between d ln HPI and ln trans n. Since both variables are integrated of order 1, the standard Granger causality test may produce invalid results. Therefore, the Toda-Yamamoto approach is adopted to ensure valid inference despite non-stationarity. The Toda-Yamamoto procedure estimates an augmented VAR model in levels by adding extra legs equal to the maximum integration order. Granger causality is then tested using a modified Wald test applied only to the original leg coefficients, ensuring correct asymptotic inference. Based on the VAR order selection in the previous part, a VAR4 model is chosen. Since both variables are I1, the augmented VAR is estimated with 5 legs, where an additional leg accounts for non-stationarity in the series. The first direction tests whether the past values of d ln HPI help predict ln trans n. This is done by jointly testing whether the coefficients on the first 4 legs of d ln HPI in the ln trans n equation are equal to 0. The Wald test yields an F statistic of 0.8459 with a p-value of 0.5031. Since p-value exceeds 5%, we fail to reject the null hypothesis, indicating that changes in house prices do not Granger cause transaction volumes. The second direction tests whether past values of ln trans n help predict d ln HPI. This is done by testing whether the coefficients on the first 4 legs of ln trans n in the d ln HPI equation are jointly equal to 0. The Wald test produces an F statistic of 1.2966 with a p-value of 0.2847. Since the p-value is greater than the 5% significance level, we fail to reject the null hypothesis, indicating no Granger causality from transaction volumes to house price changes. Moving on to policy implications. Bank Negara Malaysia, or BNM, plays a central role in shaping housing market outcomes through interest rates and macro-prudential regulations. Therefore, policy implications should be framed around how these tools affect long-run house price trends and transaction volumes, consistent with our empirical findings. Our ARDL results showed that transaction volumes respond strongly to sustained changes in house prices. For BNM, this implies that maintaining long-run price stability rather than reacting aggressively to short-term housing fluctuations is crucial for ensuring a stable and liquid housing market. Since no short-run Granger causality is detected between house prices and transaction volumes, abrupt interest rate changes are unlikely to generate immediate or predictable housing market responses. This suggests that BNM should adopt gradual and well-communicated policy adjustments to influence long-run expectations rather than short-term behavior. The relatively large error correction term, or ECT, indicates that the housing market adjusts quickly back to equilibrium. This suggests that BNM does not need to intervene aggressively in response to temporary deviations, as the market has a strong self-correcting mechanism. Since short-term changes in house prices do not establish a stable long-run relationship with transaction volumes, macroprudential policies should not be used as short-term market stabilizers. Instead, BNM should apply tools like LTV and DSR to manage long-term financial stability risk, such as excessive household leverage. Because housing transactions respond mainly to long-run price movements, clear communication by BNM is essential. By shaping expectations about future policy direction and housing risk, BNM can influence market behavior more effectively than through short-lived interventions. Overall, our findings suggest that Bank Negara Malaysia should focus on long-term stability rather than short-term market control. The housing market adjusts quickly on its own, and transaction volumes respond mainly to persistent house price trends. Policies aligned with these dynamics are more likely to be effective and sustainable. Thank you for listening to this presentation.